Start it back up. Zoom it out.
All right. Let's answer that last question right now. I want to explain to you why we even care. This is a bit of an antiquated reason. Can't see that yet. How's that look in the camera? Is that decent? Maybe we go the lights. That's decent. Oh goodness, it's already auto moving. Let me do this too. There we go. Back up. Oops, other way. That's good. All right. This is the reason that last step is there. Back up. You saw something similar to this in 243 if you took it with me. If you've got a symmetric binomial distribution, and it's perfectly symmetric means p is 0.5, which is what you guys assumed the pennies were in the beginning. And n is 3, which means I had you spin the pennies 3 times. The curve would look like that. There's a 12.5% chance you get absolutely no heads. There's a 12.5% chance you get exactly 3 heads. And there's a 3/8 or 37.5% chance you get either 1 or 2 heads. This hopefully rings a bell. In my class, we used this when we looked at my son and his Crocs. If you remember that little experiment we did in class last term. Is Max guessing when he puts his Crocs on? We looked at this curve. Actually, we didn't. I lied to you. We looked at one of these curves. There's a sample size of 5. Right there. Right there is your sample size. That's what your curve. And this auto adjust. That's your curve right there. When I told you to spin your penny 10 times. That was the curve we were comparing it against. Because there's that chance, 1/2 to the 10th power, that you got no heads, 1/2 to the 10th power that you got all heads. And everything in the middle, on average 5. On average 5. So, as you keep going, what do you notice about these curves as sample sizes get larger and larger and larger? What happens to the binomial curves? Say that again, Amy. They get skinnier. The lion's share of the data happens at the middle. It gets really, really hard if you flip a coin 100 times to get no heads at all. Or conversely, to get 100 heads. The lion's share of the data is happening in the middle. Now what does that curve look like? What's it look like? Yeah, hell yeah, it's a standard normal curve at that point. The average, right in the middle. Standard normal curve. Beautiful. So, if that value of p is 0.5, like we said, and n goes off to infinity, it looks like a bell curve. But here's the limitations of that. That's assuming that p is 0.5, 50%. What if it's not? What if it's something else? We're making an assumption that this penny is spinning at 50%. What if it's 40%, or 30%, or 20%, or 80%, or some other percentage? Well, we have a fix for that. That's what it would look like at 0.5. But if you start shifting it, there we go. Now I'll let the automatic work. Look what happens to your bell curve. Or look what happens, if you will, to the symmetry of your binomial. That's kind of a silly thing to call it, isn't it? What's happening to your symmetry? It's becoming asymmetric. It's becoming skewed. Which means that bell curve that we like to use so much from 243 goes away. We lose it. It's gone. Now it's this crazy exponential looking thing, or tilted or squashed, if you will, bell curve. So we lose the symmetry. So how do we fix that? And here's the deal. Here's the deal. There's your highly skewed curve when your sample size is 20. There's your highly skewed curve when it's 40. And look what happens right now. Look what happens as your sample size is increasing. As your sample size is increasing, oops, back up to this last one. As your sample size increases, even when you had a highly skewed curve to start, if you draw more and more and more samples, what happens to the resultant curve? What do you get back? You get back your bell curve. That explains this. When you have a large enough sample, it doesn't matter how small these guys are, you can check that box off. You can check that box off because you get your bell curve back. More on the bell curve momentarily. Some of you might be wondering, why are you talking about a bell curve? He was just talking about a binomial distribution. Why is he talking about a bell curve? I promise I'll get into that when we discuss Lipton's margin of error. I promise you. But this is the deal. This is the deal. The larger your sample, it doesn't matter how skewed this is. Now you got to realize something too, friends. There's curve over here. There's curve over here. I mean, think about it. You sampled 100, right? There's 100 samples represented here. This curve stops at 20. There's 21 through 100 on this side. But what exists over there? How much of the data is over there? What do you think? How much of the data is actually over there? Percentage-wise? Very little. Give me a percentage.
2%.
Yeah, 2% or less, exactly. And think about why. If the proportion is actually 10%, and you sample 100, what's your average? What's your average? 10. Look at the bar. It's the tallest bar. And it has to be, because 100 sampled at 10% gives you 10 on average. And then you start plussing and minusing, and you go out 2/3 and 95%. Remember your bell curve? Your bell curve approximate standard deviations. So you go out to 2/3 one standard deviation, you grab 95% at 2 standard deviations, you grab 99% at 3 standard deviations, and all of a sudden you realize, sure, there's stuff out here, but if your percentage is 10%, would you expect 80 successes out of 100? Of course not. You would expect 10% success out of 100, not 80. You'd expect 90% failure out of 100. Is that believable? Is that ish believable? Getting there? Maybe good. I just wanted to make sure why that somewhat mysterious regulation of NP and NQ both having to be bigger than 5, why it makes sense. So ish fair. Ish fair. All right. Let's close this down for a second. We'll come back there.
Start and stop again.